All right, so before we jump into today's topic, a couple quick things. First, if you want to do any corrections, those are due tomorrow night. So make sure you get those in. If you want the 2 points for an extended response, because you don't want to do the work though, just when you open it up, type into either the honor code or one of the answer boxes. I want my 2 points for this question. And if you do that per question, you can do that like 3 times. But I'll just then know to add the points, right? Now someone did ask about like my strange cryptic message about multiple choice question rescoring. So I wanted to go over that real quick. So what I said is you'll get your average score multiplied by the number of questions you choose. So let's say that you had 10 out of 15 correct. This would mean your multiple choice average is 0.67, let's say. It's 0.66 repeating, right? I think that's right, because it's 2/3. Then you would multiply this by 3.33, and this gives you a number like 2 point something. Calculator? 2 point what? 2.23. All right. So this is your average multiple choice value. Okay. Now, if you look at 5 multiple choice questions, the maximum points you could get, this would be equal to 5 times 3.33. And that's 16.65. Okay. Now you, though, for 5 multiple choice questions, your base, like what you would have scored on average on 5 questions would be 5 times 2.23, which is what, 11.06. No, 11.15. Sorry. Is that right?
Yeah.
Okay. So notice that this was the maximum you could have gotten. This is your base score. So the difference between these two is 5.50. So if you redid the multiple choice part and you got all 5 questions right, this would be your new score. This was your base. That's the difference. Divided by 2 is 2.25. Is that right? No, 2.75. So this is how many points you could get back on 5 questions. Right? And then if you did 10 questions, you could get double that back, which would put you at 5.5. And then if you did 15 questions, you could get triple that to make it like 9, 8 or something, 8 point something. Right? But that's the idea. Does that make sense? So if this number, if you got less right, this base number gets smaller, which means you can get more points back. Is everyone okay with that? Does that help? Does that make more sense? Yeah.
Can we still trade in 10 tokens and just get 2 points back for the multiple choice?
I don't have that in, so I can add it. You're the second person that's asked about that, so I'll put that into the thing. But I don't know where you would put that into. I don't have I guess you'd have to email me. All right, I'll put an announcement about it.
Thank you.
Yes. Any other questions? I think the point of really diminishing returns on that is if you have 12 or 13 correct or something, it's somewhere up near that number. It's like, oh, I traded in 10 tokens for like half a point or something. So it's not. Any other questions? Okay, then let's move ahead and let's talk about Ford. And this is I don't know if you people have ever read The Far Side, but it's this funny odd comic. And this is what whenever I talk about torques or like rotation, this is what I always think about. It's counterclockwise, right equal, always counterclockwise. And that's how it's like, oh yeah, positive direction is always counterclockwise, right? And the other guy's running the other direction from all the other. So that's why it's like, oh yeah, counterclockwise is always positive, clockwise is negative. But we want to introduce the concept of torque. So, torques are going to be torques are going to be related to rotational motion. So just like we said when we talked about accelerations, we said forces caused accelerations. So if we had like a block and we push on the block with the force, the block changes motion because of the force. Well, rotational accelerations, or alpha, cannot occur without a torque. So basically a torque is going to be a force that's going to cause a rotation, a change in rotational motion. Now to demonstrate this, I'm going to try and use this door. Because I assume all people have used a door at some point in their life. Okay, so a door, it moves, it rotates, right? It's an object that rotates, and it does so about the hinge. Is everyone good with that idea? Cool. Now, if you've ever pushed on a door, you should have noticed this. And if you haven't, go home, go back to your dorm or wherever and practice this when no one's looking. But based on where you push on the door, you get different outcomes. So if you push really close to the hinge, is it easier or harder to get the door to move? It's harder. So for the same force here, if I push way out here, the door easily moves. And you can see it's moving, which means this is some kind of rotation because theta changed and it has some omega, some rotation rate when I push out here. So our first takeaway from looking at a door is that somehow the torque is related to the distance I am from this hinge, from the rotation point. So somehow the distance is related to that torque value. Is everyone good with that? So distance makes a difference. The next thing we want to think about is how hard I push makes a difference as well. So if I push out here at the same point, if I push lightly, there's a small change in the rotational motion. If I push with a bigger force, the door has a larger larger rotation rate, right? So obviously how hard I push makes a difference. Now the last one isn't related to the hard of my push, but kind of how did I push? So the how has two parts. The strength of the push and the angle at which I apply. So if I come in here with a glancing blow and I'm pushing at some angle into the door, it's not as effective as if I plant my hand at a right angle to the door. So the angle of application is important. Matter of fact, there's an angle I can push on the door that doesn't cause the door to move at all. If I push out here on the side of the door or along this part of the door frame, this will not cause a rotation, right? So where you push and how you push makes a difference in terms of the rotation, which is related to the torque. So let's look at this. So we said where you push, I can spell, where you push, this is what we call R. This is the distance from rotation point to place that force is applied. Sadly, this is called the radial distance, but it is not the radius. But it doesn't have to be the radius. All it is it's that distance from wherever the rotation is happening to where your force is applied. Is everyone okay with that? So on my door example, when we were pushing when we were pushing out here at the handle is 84 centimeters away. I don't divide it by 2 to make it a radius. It's just 84 centimeters, right? So you don't always have to divide it by 2. Now, if they give you the diameter, you may have to divide it by 2. But for like a distance, you might not have to. So this is where you push. The second part we said is how you push. And the how, my gosh. How you push. This is related to the force, the strength of the push, and this angle phi. This is the angle between R and F. All right. So how this plays out? If you think about, like, I have a picture on the next slide as soon as I'm done with this. If we have some kind of wrench trying to turn this bolt here, the idea is the bolt will turn about its center. If I apply a force, this is my distance R, I apply some force here to the handle. Now, the angle between R and F is right there. That is phi, the angle between R and F. And what happens is this piece right here, this blue part, is F sine of phi. And what we're going to see is it's only the part that is perpendicular to R, only the part of the force that is perpendicular to R that contributes to the rotation. Which is why when I pushed on the edge of the door, there was no rotation. All right, so this is my example here. And it turns out that torque then, we give it a Greek letter tau. This is torque. It's R F sine phi. So it's the distance and the how you apply it piece. Right, the force times that angle between them. So sine of 90 is 1. Right angles get the most out of the application. Is everyone okay with that? Now, the other thing to take out of this, torque has units of Newton meters because it's a force and a distance. So torques are Newton meters, right? In American units, it's foot pounds or feet pound or pound feet or however they say it, foot pounds of torque. Because feet and pounds are measurements of forces and distances. Is everyone okay with that? All right. So let's try this then on a learning catalytics question. So I delivered a cool question. And you can need about 4 more people to respond. All right, now we need 5 more people. Wait another minute. All right, does anybody else, someone having connectivity issues or? You should be able to answer them before I close this out. Okay. All right, so when we're looking at this person pulling on the rope, in the first case, we'll just measure from the box just to keep it easy. They have some force applied here at some distance r, and we noticed that in the picture they made sure that that was a right angle. They showed that as a right angle so that we see torque is RF sine phi. Now in the second picture, the R didn't change, did it? Was R was the same in the second picture, right? The angle is still a right angle, and the force, they said, was the same force. So did the torque change on the second picture? Because torque would be RF sine phi. Are these two torques different or the same? They're the same. So adding the rope and pulling from farther over here doesn't change the force or the distance or the angle. So it did not change the torque. Is everyone okay with that? Now we can ask the follow-up is everyone okay with that before I asked and then I just skipped right over it. But are people okay with that, or is there something that? So all right. So how could we make the torque bigger then? What could we change? Can you change his strength, the force? Yeah, I guess he could go hit the gym for a while, then get stronger and then come back and try pulling on it. But let's say he had to get this, he needed to move that bolt today. What could he do which variable is left to change that? R. So how could he could what? He could move further away, increase R, and then he could generate more torque. How many people have ever enjoyed changing a tire? A few people, okay. So when you've enjoyed that experience, you take your tire iron out, you put it on the bolt, the lug nut, and you go to, and then the tire just kind of waves with it a little, and it's like a bouncy effect, right? And then you really start digging and you start bouncing up, trying to get that thing. Someone's like, oh, I try stepping on it. I was like, don't try stepping on it. But it doesn't move. So has anybody had that problem? And then what did you do? You're like, I call AAA. So what you can do is you can do what? You can put what's called a breaker bar over the tire iron. And a breaker bar is this tube that goes over the tire iron and extends the radius. That gives you a larger radius. By extending up to here, you've made R bigger, you generate more torque. And then you can loosen up those lug nuts. Now, the only thing I always tell people is when you do that, spray them with some WD-40 or some kind of thing that'll penetrate into the threads so you don't shear the bolt head right off the nut. But that's how you can do that is those are called like breaker bars or something to extend that. You can get a longer handle wrench or something so that you can buy. Now, that might be more expensive, but that's one way you can do it too. If you ever have to like crank on something with like a wrench and a ratchet, then you could get a longer handle and that will generate more torque. You can do the same with your socket wrench. You could put a bar over it and extend it, get more torque. All right, is everyone okay with that idea? Because usually changing R and F are the only two ways to do it. Okay. So we did that. Here we go. So let's practice calculating one time with our new equation. So we have this tire that they tell us what about this tire? What's one of the numbers they give us? What? It's the force. So they tell us this force is here and this force is 15 meters. What else do they tell us? Diameter. The diameter is 26 centimeters. Okay, so then we imply that the radius is 13 because radius is half the diameter. All right, and they want to know the torque. Now, there are a few things that we have to talk about related to wheels. You've never thought this much about a wheel before. But all the points, so let's just look at this. So a wheel rotates about what point in the wheel? It's obvious, but it's the axis, the center of the wheel. So whenever we talk about a circle, a hoop, a disc, a cylinder, a sphere, a hollow sphere, anything that is spherical or cylindrical or circular like in nature, those things will rotate about their center. All right. So that's something you never think, yeah, but okay, yeah. Thanks for stating the obvious. But if we don't, then you won't think about it. Now, the next part is that all points on the edge of the circle are what from the center? The same distance because they're all at R away. And all points on the edge of the circle are tangent to the circle at the point. So at every point, this is a right angle to the radial distance. So whenever a force is applied to an edge of a circle, you can assume, unless otherwise stated, it is a right angle that the force is applied at. Unless they come into the problem and tell you this force was applied at some angle to the edge of the system, you assume it's a right angle. All right, because most of the time they will be at right angles. Because it takes effort to change the angle on your force application on a wheel. Is everyone okay with that? All right. So what does this mean? This means that this rotation center is here. The R that we use is the 0.13 meters because all of our units are always kilograms, meters, and seconds. So when we go to calculate our torque will be 0.13 15 sine of 9. Bless you. These things. All right, so we got 1.95, and that's Newton meters. But we have one last thing. Which way would my force cause this to start rotating? Is it going to go this way or this way? It'll go down. This is negative, this is positive. So my torque will cause us to move in the negative direction. Is everyone okay with that? Okay. Okay, all right, then let's up it, make it a little more interesting. So now what we want to do is we want to look at what happens when we have multiple torques acting on our system. So now let's take a look at a couple different torques acting. Good position. So if we have two different forces acting. So here's our lever arm. They tell us that force 1 is here. And this, we'll just mark this way. Force 1 acts at R1. Because every force has its own distance that it is applied to. So this is R1. It goes with F1. And here is phi. So for each torque, it will have its own radius, force, and angle. Now, torque force 2, which will generate torque 2, sits right here. And force 2 will have phi 2, and it will sit at R2. Is everyone good with that? All right. So then, once we have our rate distances, forces, and angles, what we do is we come in and say, well, torque 1 is R1, F1, sine of phi 1. And we can get a value. Unless we're looking for one of those, and then we stop with that. Then torque 2 is R2, F2, sine of phi 2. So we calculate torque 1 and torque 2. Now, when we think about adding our torques up, we sum up our torques. Well, we get torque 1. Now, when we're thinking about this, we said this way is positive and that way is negative. So when we add up our torques, we see that torque 1 wants to go this way, but torque 2 wants to go that way. Because we can always think about this blue one is F1 sine of phi 1. Notice the force is pulling it that way. And the blue part here, this is F2 sine of phi 2. The blue part is pulling it that way. Right? So then it would be torque 1 minus torque 2. And remember when we were talking, initially we were talking about like boxes and two different teams pushing left and right on a box. This is no different, except when we look, it's, oh, positive is this way, negative is that way, right? And so what we're looking at is torque 1 wants to push the box to the right, torque 2 wants to push the box to the left, except now it's going to cause it to spin instead of slide across the surface. So if torque 1 is larger than torque 2, we start to rotate that way. If torque 2 is larger than torque 1, we start moving this way. And if torque 1 equals torque 2, the object just stays still. And when things stay still, we call that what? Equilibrium. So that's called a rotational equilibrium when things don't rotate, right? Is everyone good with that? So we have, just like before with forces, we can add up our torques in a system. Now, the fun part is we want to do this next. I think it's on my next slide. Let's find out. It is. Nice. But we also have to think about, oh, we could flip the wrench to the other side. And how does that change anything? So let's take a look. So if we flip our wrench, what happens? So now we come over here and our wrench is on this side. We have force 1 here, the same thing. Force 1 exists at R1. It has its angle phi 1. And we have force 2 and R2, and here's phi2. Is everyone good with that? All we did is we took the wrench, flipped it to the other side. Is everyone good with that? We end up getting the same torques. But what I want to point out is this now. Force 1 will cause a rotation this way. Force 2 will cause a rotation that way. Because now force 2 sine, so let me write this in. And here is, that's F1. So this now wants to pull it this way. Force 1 wants to pull it that way. So is this torque positive or negative?
Negative.
This is negative. This one is positive. Because when we look at the giants, when we think about this as a circle, this would be continuing this counterclockwise motion. So this is clockwise, sorry. This is our clockwise motion, it's negative. This one contributes to the counterclockwise motion, so this is positive, right? So we always just have to pay attention to which way is our system going to spin, and that is how we put on the plus and minuses. All right? Is everyone good with that? Now, the only other thing I want to mention is this idea that I kind of mentioned just a second ago, is the idea of thinking about all the different torques adding up on the system. And there's two categories we can put them in, clockwise, counterclockwise, right? So anything that, when we're looking at summing our torques, we can think about all of the torques that go counterclockwise minus all of the torques that are clockwise. And that's it. Because then whichever, if this has two or three different, like in my example, each one of these had two torques in it, right? But whichever team has got the bigger value, that's the way the system will start rotating. Unless all these add up to 0 and then you're just sitting. Is everyone good? But I want you to think about this in terms of, oh, all I have to do is find all these, add them up, then take the difference. Okay? So this is much, in one way, it's much, there's no X, Y, Z, it's just clockwise, counterclockwise. We have two categories, right? And that's it. Is everyone okay with that? All right, then what we'll do is we'll do another sample problem, but now we'll put two torques in. But I want to use my cool thing I brought in. So whenever we're thinking about torques, we can think about something like this. So this is a lot like that problem, even though you're like, no, it doesn't look like that to me at all. But this is like my pivot. That black dot is my pivot. So here's my pivot, right? And so the idea is whichever side has the larger force, the larger torque, that is the way it will start rotating. So I hold it in balance, and then obviously there must be more torque on this side because it starts rotating that way. But if I move this position, I throw this in here, I've changed the torque value. Now this torque is bigger, right? And so what's causing the torques? What force is causing the torque on the beam, on the beam? Because I have to put in R, so this is R, here's an R. What force is causing this rotation? What is pulling down on the little hangers? Gravity. So weight. The weight of the hangers themselves is causing the rotation. Take off the hangers just momentarily. And we balance this. Oh, it's not 7. But if I balance this ruler, this thing on its view. But if I balance this ruler, there's no torques on it. So if I put my pivot in the middle where the ruler is, because the middle of the ruler is where the mass of the ruler is located. All right, so if I put my finger underneath it, well, except for this metal hook. But if I put my finger underneath it or hold it like this, it balances because the pivot is located where that center of gravity is. Now, if I move my pivot, so the 50 centimeter mark is about where the center of gravity is. If I move my pivot off center of gravity, there is now a torque generated because the weight of the ruler is here. And there's a distance. So if R isn't 0, you can generate a torque against the object itself. All right. But if I put my pivot underneath the center where the center of gravity is, there's no rotation because R is 0. Is everyone good with that idea? So if your pivot is where the center of mass is, then there's no rotation, which is how the old like scale systems worked in the old days, or teeter-totters, are balanced. And then you put the kids on the teeter-totter, and then the kids cause the teeter-totter to go one way or the other, depending on the kids. Is everyone good with that? So if I put a little bit of mass over here, this will do what? Because I put the kid and then the kid fell off. So hopefully there's time. But the idea is that this generates a torque that pulls that direction, right? So torque's about a center. And notice in this case, even in this case here, when I have these two masses, both of them point what? Down. But they're causing rotations. One is clockwise, one is counterclockwise, even though both forces are down, right? So that's something else to notice is the direction of the forces isn't what determines the torque. Is it going to cause it to rotate clockwise or counterclockwise? So let's try to draw this up and solve this problem. Okay. All right. So we have our beam here. They tell us the center of rotation is right there, and that F1 here is equal to 10 newtons. They tell us F2 is equal to 8 newtons. Now, whenever something is hanging and there's a torque, let's say like from these weights on the beam, the weights act at what angle? 90 degrees. They act at right angles initially, right? So these are at right angles. Now they tell us that this force 1 is 60 centimeters away. And even though it's called D1, we don't divide it in two. That's just saying a distance, right? Because this is the physical distance that is away. So we know that R1 is 0.60 meters. And they tell us R2 is 0.40 meters. Is everyone good with that? So when we go to get torque 1 is 0.6 times 10 sine of 90. And torque 1 is 6 Newton meters. Now torque 2 is going to be our 0.4 times 8 sine of 90. So torque 2 is 3.2 Newton meters. Is everyone good with that? Now, when we go to look at we have to sum our torques. We look in and say, well, this one would cause the system to rotate this way. And is this clockwise or counterclockwise? Counterclockwise. We know this is going to be positive, and on this side, it's going to cause a what? This is clockwise, so it's negative. So we see that it is torque 1 minus torque 2. So the sum of our torques is going to be 6 minus 3.2. That gives us 2.8 Newton meters. Is everyone good with that? So we should be able to sum up some torques on different configurations of different objects. All right. Most right now, there will be beams like this or wheels. Those are our two favorite shapes at the moment. Is everyone good? All right. So what we want to do is we want to shift gears for just a moment. And we want to introduce a topic called center of mass. And the center of gravity or mass is like if you took the whole object and you concentrated the mass of the object into one single point. So for the ruler, we said the whole center of mass, the whole mass of the object acts as though it's sitting here at that 50 centimeter mark. And that's why I said, hey, if I take off these things, I can take this ruler, put it on my finger, and because the center of mass is underneath my finger where the pivot is, R is 0 in the torque calculation, it generates no torque. But if I move the ruler a little bit to the side, the center of mass now has an R and the object will rotate. So another way to talk about this is if the center of mass is inside what we call the base of the object, so my hand is the base, and now I can move the center of mass around, and as long as the 50 centimeter mark is inside of my hand, there's no torque. But if that 50 centimeter mark is just slightly outside, it will rotate. So the idea is that the center of mass is also related to the stability of a system. If the center of mass is underneath the base, which is where the object can't cause a rotation, then your system is stable. But if that center of gravity is outside of that base, your system will rotate or go into motion. It's not stable. And two examples I want to bring up of that. One is with a related to a forklift. So whenever you see a forklift, initially these are designed with two concepts in mind. They put most of the mass of the forklift at the back end and near the bottom. And what that allows you to do is if they take and lift something heavy up, it prevents the center of mass from shifting outside of the base, right? So unless they try lifting something very massive, more massive than the forklift, and then they raise it up high, then that would cause the forklift to tumble. But as long as they don't do that, they're okay. And this also goes to another concept that hopefully you don't do. You don't put your heaviest objects on the highest shelf, right? Because that shifts the center of gravity high on the shelf and it makes it more unstable. Is everyone good with that idea? All right. Now the other one is more applicable to people. And this has to do with the fact that center of mass of people is usually in your midsection. And so the idea is that as long as your center of gravity is between your feet, you're stable, right? You can, hey, my center of gravity is, and even if you ever notice, whenever you go up on one foot, usually you shift a little bit to move your center of gravity underneath your 1 foot. Does everyone make sense, right? Now, what happens though is you get older, you start doing this. You start usually hunching over more as you get older. So what you grab is you grab a walker. And the walker makes your center of your base much larger, and it enables you to safely walk. And my example I give of this is the following. This is something you can do with your friends this weekend or something, maybe at a holiday with your family. You stand them up against a wall, and then with their feet and butt against the wall, you ask them to touch their toes. And I guarantee you, it's very, very difficult. Because as you go to bend over, what will happen is you can't bend yourself in half. Now, there's been a few students that I've seen do it. They can like literally fold themselves vertically in half somehow. I don't know. Maybe they have missing organs or something. But the idea is what normally happens when you go to touch your toes. Your butt normally shifts back to keep your center of gravity underneath you, underneath your base. But when you're up against the wall, you can't shift your center of gravity backwards, right? So that's the idea. This is also why if you've ever enjoyed carrying a heavy backpack, you slouch over a little bit because the book, if you didn't, the book bag would pull your center of gravity and you just like flop backwards, right? You've naturally done though, your body naturally does that to keep you stable. And I always joke, this is the whole concept of football because you have a center of mass and it's between your feet. And when someone goes to tackle you, their goal is to knock your center of mass outside of your base, causing you to go to the ground, right? Fundamentals of football. So this is the idea of center of gravity. It's actually very important for buildings and things like that. They have to know and understand how those are. Cars, have you ever seen those cool warning signs in the car? Hey, this car can flip on high, at certain turns and things like that. It's because the center of gravity is high in that vehicle and it can tip over. All right, but what we want to do real quick with our remaining few minutes is we're going to talk about how we can calculate a center of gravity of an object. The one really awesome application that I never talk about is actually for planets. Oh, this clicker doesn't. Oh, is it off? Is that no? No. All right. It's actually one of the ways you can determine like properties about planets and stars. All right, so let's take a look at center of mass. So our equation for center of gravity, xg, it goes something like this: the sum of the mr over the sum of the m's. So the idea is we look at the masses and some distance they are from a point we choose. We add up all the masses and all the distances that they are from our center point that we pick, and we divide by the total mass. And what this does is this points us to where the center of mass is. So let me try to demonstrate with these two masses. So we have two masses. One is 5 kilograms. The other is 3 kilograms. And they are separated by a 7-meter distance. And whatever's connecting them is a massless rod, a rod of negligible mass, as they would say. Now, when you're calculating the center of gravity, you always get to choose the point you're going to measure from. I always recommend you you could put it here, but the idea is you put it at the leftmost bottom left point that you can and measure all distances positive when you can. It just makes things a little easier. So how would we put these into our equation now? Well, xg is going to be mass 1. But how far away is mass 1 from my origin? It's 0. It's sitting where my blue crosshair is. So it's 5 times 0. Now the second mass is 3 at a distance of 7. And then I plug in 5 plus 3. Because I measure all my R's from wherever I put my choice, this is my choice. All right. But it doesn't matter where I pick, wherever you calculate from will point to the same spot in the system. It doesn't matter. All right. So what we see is xg then is 21 over 8, which ends up being like 2 5/8. So if this is in the middle is 3.5, our center of gravity is somewhere like right there. Now, quickly, if we would have picked over here, that just would have made our distances negative. But notice the 0 would be on the 3 now, and the 7 would be on the 5. And so that would be 35 over 8, which means it puts you somewhere halfway past here. It'll still land you there. So it doesn't matter where you pick the blue crosshair to calculate from. It'll always point you to the same spot in the system. It's just it'll give you a different value, which is why a lot of times in these problems, they'll tell you, put the calculating point here. Otherwise, the number becomes arbitrary. But this allows us to calculate where the center of mass of a system is, right? And so just so you know, like on the Earth Sun, the center of mass between the Earth and the Sun is slightly shifted off the center of the Sun because the Earth pulls it just a little bit off the center of the Sun. But it's still inside the Sun. All right. But it causes the Sun to have a wobble to it, right? All right. So I will see you guys on Monday and enjoy your weekend. I'll post an announcement about those 10 points for 2 points on the multiple choice.